Real-time messaging protocol was initially a proprietary protocol developed by Macromedia for streaming audio, video and data over the Internet, between a flash player and a server. Macromedia is now owned by Adobe, which has released an incomplete version of the specification of the protocol for public use. The RTMP protocol has multiple variations. The plain protocol, which works on top of and uses TCP port number 1935 by default. RTMPS, which is RTMP over and TLS-SSL connection. RTMP, which is a TMP encrypted using Adobe's own security mechanism. While the details of the implementation are proprietary, the mechanism uses industry-standard cryptography primitives. RTMPT, which is encapsulated within HTTP requests to traverse firewalls. RTMPT is frequently found utilizing clear text requests on TCP ports 80 and 443 to bypass most corporate traffic filtering. The encapsulated session may carry plain RTMP, RTMPS, or RTMPE packets within. While the primary motivation for RTMP was to be a protocol for playing flash video, it is also used in some other applications, such as the Adobe Lifecycle Data Services ES. Basic operation: RTMP is a TCP-based protocol which maintains persistent connections and allows low-latency communication. To deliver streams smoothly and transmit as much information as possible, it splits streams into fragments and their size is negotiated dynamically between the client and server, while sometimes it is kept unchanged. The default fragment sizes are 64 bytes for audio data, and 128 bytes for video data and most other data types. Fragments from different streams may then be interleaved, and multiplexed over a single connection. With longer data chunks, the protocol thus carries only a 1-byte header per fragment, so incurring very little overhead. However, in practice individual fragments are not typically interleaved. Instead, the interleaving and multiplexing is done at the packet level, with RTMP packets across several different active channels being interleaved in such a way as to ensure that each channel meets its bandwidth, latency, and other quality of service requirements. Packets interleaved in this fashion are treated as indivisible, and are not interleaved on the fragment level. The RTMP defines several virtual channels on which packets may be sent and received, and which operate independently of each other. For example, there is a channel for handling RPC requests and responses, a channel for video stream data, a channel for audio stream data, a channel for out-of-band control messages, and so on. During a typical RTMP session, several channels may be active simultaneously at any given time. When RTMP data is encoded, a packet header is generated. The packet header specifies, amongst other matters, the ID of the channel on which it is to be sent, a timestamp of when it was generated, and the size of the packet's payload. This header is then followed by the actual payload content of the packet, which is fragmented according to the currently agreed upon fragment size before it is sent over the connection. The packet header itself is never fragmented, and its size does not count towards the data in the packet's first fragment. In other words, only the actual packet payload is subject to fragmentation. At a higher level, the RTMP encapsulates MP3 or AAC audio and FLV1 video multimedia streams, and can make remote procedure calls using the action message format. Any RPC services required are made asynchronously, using a single client-server request-response model, such that real-time communication is not required. Encryption: RTMP sessions may be encrypted using either of two methods, using industry-standard TLS-SSL mechanisms. The underlying RTMP session is simply wrapped inside a normal TLS-SSL session. Using RTMPE, which wraps the RTMP session in a lighter weight encryption layer. It is generally understood that the TLS-SSL handshake at the beginning of a session is very computationally intensive. Adobe developed RTMPE as a lighter weight alternative, to make it more practical for high-traffic sites to serve encrypted content. Adobe advertises RTMPE as a method for secure content delivery, protecting against client impersonation, but this claim is false. RTMP only uses anonymous Diffie-Hellman, which provides no verification of either party's identity, and as such is vulnerable to trivial man-in-the-middle attacks at session initialization. HTTP tunneling. In RTMP tunneled, RTMP data is encapsulated and exchanged via HTTP, and messages from the client are addressed to port 80 on the server. While the messages in RTMP are larger than the equivalent non-tunneled RTMP messages due to HTTP headers, RTMP may facilitate the use of RTMP in scenarios where the use of non-tunneled RTMP would otherwise not be possible, such as when the client is behind a firewall that blocks non-HTTP and non-HTTPS outbound traffic. The protocol works by sending commands through the postal and AMF messages through the post body. An example is post 1 HTTP/1.1. For a connection to be opened. Specification document and patent license. Adobe has released a specification for version 1.0 of the protocol dated December 21, 2012. The web landing page leading to that specification notes that to benefit customers who want to protect their content, the Open RTMP specification does not include Adobe's unique secure RTMP measures. A document accompanying the Adobe specification grants non-exclusive, royalty-free, non-transferable, non-sublicensable, personal, worldwide patent license to all implementations of the protocol, with two restrictions: one forbids use for intercepting streaming data, and another prohibits circumvention of technological measures for the protection of audio, video and/or data content, including any of Adobe unregistered trademark S secure RTMP measures, patents and related litigation. Stefan Richter, author of some books on Flash, noted in 2008 that while Adobe is vague as to which patents apply to RTMP, U.S. Patent 7,246,356 appears to be one of them. In 2011, Adobe did sue Browser claiming among other things, infringement of their RTMP patents. Packet structure. Packets are sent over a TCP connection which are established first between client and server. They contain a header and a body which, in the case of connection and control commands, is encoded using the action message format. The header is split into the basic header and chunk message header. The basic header is the only constant part of the packet and is usually composed of a single composite byte, where the two most significant bits are the chunk type and the rest form the stream ID. Depending on the value of the former, some fields of the message header can be omitted and their value derived from previous packets, while depending on the value of the latter, the basic header can be extended with 2 or 3 extra bytes. If the value of the remaining 6 bits of the basic header is 0, then the BH is of 2 bytes and represents from stream ID 64 to 319. If the value is 1, then the BH is of 3 bytes and represents from stream ID 64 to 65,599. If the value is 2, then BH is of 1 byte and is reserved for low-level protocol control messages and commands. The chunk message header contains metadata information such as the message size, the timestamp delta and message type. This last value is a single byte and defines whether the packet is an audio, video, command or low-level RTMP packet such as an RTMP ping. An example is shown below as captured when a Flash client executes the following code. This will generate the following chunk. The packet starts with a basic header of a single byte where the 2 most significant bits define a chunk header type of 0 while the rest define a chunk stream ID of 3. The 4 possible values of the header type and their significance are, B00 equals 12-byte header. B01 equals 8 bytes, like type B00. Not including message ID. B10 equals 4 bytes, basic header and timestamp are included. B11 equals 1 byte, only the basic header is included. The last type is always used in the case of aggregate messages where, in the example above, the second message will start with an ID of 0xC3 and would mean that all message header fields should be derived from the message with a stream ID of 3. The 6 least significant bits that form the stream ID can take values between 3 and 65,599. Some values have special meaning, like one that stands for an extended ID format, in which case there will be 2 bytes following that. A value of 2 is for low-level messages such as ping and set client bandwidth. The next bytes of the RTMP header are decoded as follows: byte number 1 equals chunk header type. Byte number 2-4 equals timestamp delta. Byte number 5-7 equals packet length, in this case it is 0x00019 equals 25 bytes. Byte number 8 equals message type ID, 0x14 defines an AMFO encoded command message. Byte number 9-12 equals message stream ID. This is in little endian order. The message type ID byte defines whether the packet contains audio-video data, a remote object or a command. Some possible values are for R, 0x01 equals set packet size message, 0x04 equals ping message, 0x05 equals server bandwidth, 0x06 equals client bandwidth, 0x08 equals audio packet, 0x09 equals video packet, 0x11 equals an AMF3 type command, 0x12 equals invoke, 0x14 equals an AMFO type command. Following the header, 0x02 denotes a string of size 0x100C and values 0x63, 0x72, 0x60. Following that we have a 0x00 which is the transaction at a value 2.0. The last byte is 0x05 which means there are no arguments. Invoke message structure. Some of the message types shown above, such as ping and set client server bandwidth, are considered low-level RTMP protocol messages which do not use the AMF encoding format. Command messages on the other hand, whether AMFO or AMF3, use the format and have the general form shown below. String, command name, number, transaction ID, mixed, argument X. Null, string, object, key 1, value 1, key 2, value 2. The transaction ID is used for commands that can have a reply. The value can be either a string like in the example above or one or more objects, each composed of a set of key-value pairs where the keys are always encoded as strings while the values can be any AMF data type, including complex types like arrays. Ping message structure. Ping messages are not AMF encoded. They start with a stream ID of 0x02 which implies a full header and have a message type of 0x04. The header is followed by 6 bytes which are interpreted as such: number 0-1, ping type; number 2-3 second parameter, number 4-5, third parameter. The first 2 bytes of the message body define the ping type which can apparently take 6 possible values. Type 0, clear stream, sent when the connection is established and carries no further data. Type 1, clear the buffer. Type 3, the client's buffer time. The third parameter holds the value in millisecond. Type 4, reset a stream. Type 6, ping the client from server. The second parameter is the current time. Type 7, pong reply from client. The second parameter is the time when the client receives the ping. Pong is the name for a reply to a ping with the values used as seen above. Server BW client BW message structure. This relates to messages that have to do with the client upstream and server downstream bit rate. The body is composed of 4 bytes showing the bandwidth value with a possible extension of 1 byte which sets the limit type. This can have one of 3 possible values which can be hard, soft or dynamic. Set chunk size, the value received in the 4 bytes of the body. A default value of 128 bytes exists and the message is sent only when a change is wanted. The protocol. Handshake. After establishing a TCP connection, an RTMP connection is established first performing a handshake through the exchange of 3 packets from each side. These are referred in the official spec as CO-2 for the client-sent packets and SO-2 for the server side respectively and are not to be confused with RTMP packets that can be exchanged only after the handshake is complete. These packets have a structure of their own and C1 contains a field setting the epoch timestamp, but since this can be set to 0, as is done in third-party implementations, the packet can be simplified. the client initializes the connection by sending the CO packet with a constant value of 0x03 representing the current protocol version. It follows straight with C1 without waiting for SO to be received first, which contains 1536 bytes, with the first 4 representing the epoch timestamp, the second 4 all being 0, and the rest being random. C2 and S2 are an echo of S1 and C1 respectively, except with the second 4 bytes being the time the respective message was received. After C2 and S2 are received, a handshake is considered complete. Connect. At this point, the client and server can negotiate a connection by exchanging AMF-encoded messages. These include key-value pairs which relate to variables that are needed for a connection to be established. An example message from the client is: invoke, a €E connector euro, transaction ID, 1.0, object 1, app, a example euro, flash ver, a OE Mac 10, 2153, to a euro, SWF URL, null, TC URL, a OE RTMP 127.0.0.1/sample a a, FPAD, false, capabilities, 9947.75, audio codecs, 3191, video codecs, 252, video function, 1, page URL, null, object encoding, 3.0. The Flash Media Server and other implementations uses the concept of an app to conceptually define a container for audio, video and other content, implemented as a folder on the server root which contains the media files to be streamed. The first variable contains the name of this app as sample, which is the name provided by the browser server for their testing. The flash var string is the same as returned by the ActionScript getVersion function. The audio codec and video codec are encoded as doubles and their meaning can be found in the original spec. The same is true for the video function variable, which in this case is the self-explanatory support vid client C constant. Of special interest is the object encoding, which will define whether the rest of the communication will make use of the extended AMF3 format or not. As version 3 is the current default, the Flash client has to be told explicitly in ActionScript code to use AMFO if that is requested. The server then replies with a server BW, a client BW and a set packet size message sequence, finally followed by an invoke, with an example message. Invoke, a result a euro, transaction ID, 1.0, object 1, FMS VER, FMS/3, 5, 2004, capabilities, 31.0, mode, 1.0, object 2, level, a trusted user code, a OE net connection. Connect success, description, a OE connection succeeded our data, version, a A3, 5, 2004 a client ID, 1,728,724,019, object encoding, 3.0. Some of the values above are serialized into properties of a generic ActionScript object which is then passed to the net connection event listener. The client ID will establish a number for the session to be started by the connection. Object encoding must match the value previously set. Play video. To start a video stream, the client sends a create stream invocation followed by a ping message, followed by a play invocation with the file name as argument. The server will then reply with a series of onStatus commands followed by the video data as encapsulated within RTMP messages. After a connection is established, media is sent by encapsulating the content of FLV tags into RTMP messages of type 8 and 9 for audio and video respectively. HTTP tunneling. This refers to the HTTP tunneled version of the protocol. It communicates over port 80 and passes the AMF data inside HTTP post request and responses. The sequence for connection is as follows. Post ident to HTTP/1.1, content type, application XFCS/R/N. HTTP/1.0 404 not found. Post 1 HTTP/1.1, content type, application xfcs/r/n. http://1.1200 OK, content type, application xfcs/r/n, 1,728,724,019. The first request has an ident2 path and the correct replies are 404 not found error. The client then sends in one request where the server must reply with a 200 OK appending a random number that will be used as the session identifier for the said communication. In this example 1,728,724,019 is returned in the response body. Post 1,728,724,019/0 http:/1.1, http:/1.1200 OK, 0x01. From now on the session id/sequence is a polling request where the session it has been generated and returned from the server and the sequence is just a number that increments by 1 for every request. The appropriate response is a 200 OK with an integer returned in the body signifying the interval time. AMF data is sent through session id/sequence, software implementations, client software. The most widely adopted RTMP client is Adobe Flash Player, which supports playback of audio and video streamed from RTMP servers. XBMC Media Player has partial support for playing RTMP streams. Stream Transport is Windows software that can download videos that stream over RTMP. Nash, an open-source replacement for the Flash Player on the Linux platform, intends to support RTMP streaming for Linux. RTMP-DUMP. The open-source command line tool RTMP-DUMP is designed to play back or save to disk the full RTMP stream including the RTMP protocol Adobe uses for encryption. RTMP-DUMP runs on Linux, Android, Solaris, macOS, and most other Unix-derived operating systems, as well as Microsoft Windows. Originally supporting all versions of 32-bit Windows including Windows 98, from version 2.2 the software will run only on Windows XP and above. Packages of the RTMP-DUMP suite of software are available in the major open-source repositories. These include the front-end apps RTMP-DUMP, RTMP-SAV, and RTMP-SUCK. Development of RTMP-DUMP was restarted in October 2009, outside the United States, at the Player site. The current version features greatly improved functionality, and has been rewritten to take advantage of the benefits of the C programming language. In particular, the main functionality was built into a library which can easily be used by other applications. The RTMP-DUMP developers have also written support for LibRTMP from Player, FFmpeg, XBMC, curl, VLC and a number of other open-source software projects. Use of LibRTMP provides these projects with full support of RTMP in all its variants without any additional development effort. FLVSTREAMER FLVSTREAMER is a fork of RTMP-DUMP, without the code which Adobe claims violates the DMCA in the USA. This was developed as a response to Adobe's attempt in 2008 to suppress RTMP-DUMP. FLVSTREAMER will save to disk a stream of audio or video content from any RTMP server, if encryption is not enabled on the stream. Server software. Some full implementation RTMP servers are, Adobe Flash Media Server, Adobe Lifecycle Data Services, Amazon S3 and Amazon CloudFront can stream using RTMP. HAWXE Video is a multi-thread FLV streaming server entirely written using the Hague's programming language. Real Networks Helix Universal Server can support RTMP, RTMPT and RTMPS streaming for live and on-demand content. Red 5 Media Server is a Java open-source project which delivers a powerful video streaming and multi-user solution to the Adobe Flash Player and other client technologies. Video has wide functionality, not only file streaming, but restreaming of MPEG-TS or Shoutcast to Flash clients using RTMP. Unreal Media Server supports live RTMP streaming, in real-time and buffered modes. As a streaming engine, WebOrb Integration Server, free switch RTMP media streaming available with mod RTMP and allow interconnecting with other VoIP protocols etc. FFmpeg, links with RTMP module, XSPLIT broadcaster, see also, RTMP DUMP, protected streaming info about RTMPS and RTMPE, real-time media flow protocol, based on UDP, video on demand, references. External links, Adobe Developer Page, RTMP, Official Specification, OS Flash, RTMPOS.